Hello.
Yes, sir.
Okay. Okay, so in the last class we started looking at the forced convection, concept of forced convection. Uh, we said that in the forced convection, when the turbulence in the fluid is imparted by a mechanical element, uh, usually if you wanted to solve the problem, we can make the energy balance from the first principle. We can get the differential equations and uh, easily, but the problem is how to solve these differential equations. So it's not easy to solve these differential equations because very often the problem becomes mathematically intractable. Okay, so again, how to deal with such situation? To deal with such situation, we then use the concept of heat transfer coefficient, where heat transfer coefficient can be obtained. Coefficients can be obtained from the empirical correlations. Although there is a error of 25 to 30%, but it enables solving the problem much more easily compared to solving it using a first principle approach. Okay. Again, we have again talked about the, even though if you are doing a some first principle balance, in such cases you will see that we will be assuming a thin film near the flat surface, isn't it? And we in general assume that the fluid is stagnant in this, the layer which is very close to the surface of the wall. Okay, but in a real life there is no such film which is having a complete the fluid which is completely stagnant is not there in the real life film. Okay, so this concept of boundary layer then comes into the picture. So this concept of the boundary layer comes into the picture because you can see that in this boundary layer the velocity changes, isn't it? It starts from zero and then reaches to the free stream velocity, and the velocity profile of this boundary layer has a profound impact on the transfer coefficient. Okay, so that's what we started. Then we have started looking at the concept of boundary layer. We said that if the fluid flow past a flat plate like this, isn't it, then we will have a boundary layer which is shown by a red colored line here, isn't it? So as our distance from this leading edge increases along the flow direction, you can see that initially I will have a laminar boundary layer, then I will have a transition zone, and after the transition zone I will have a turbulent boundary layer. Okay, so here you can see that the thickness of this boundary layer increases along with the increase in x. The critical Reynolds number in this case is 5 into 10 raised to the power 5. If Reynolds number is less than this particular value, in that case the flow is laminar. Between 5 into 10 raised to power 5 and 10 raised to power 6, the Reynolds number, if the Reynolds number is between these two limits, then the flow is basically comes into this transition zone, and beyond 10 raised to the power 6 the flow is turbulent. Okay, in this case again what we have discussed is Reynolds number is calculated as rho v x by mu, where x is the distance from the leading edge. That everybody has to remember. So this x is used as a distance here. That's why it is, this Reynolds number is designated as rex here. So this thickness of the boundary layer and the velocity profile within the boundary layer is extremely important, because that is going to give you a different value of heat transfer coefficient. In fact, if you move from this leading edge, you will have a different value of heat transfer coefficient. But very often we represent this entire system using a average heat transfer coefficient. Okay, all right. Again, similar to the velocity boundary layer, a similar boundary layer we can see for a temperature, which we call it as a thermal boundary layer. This thermal boundary layer and the momentum boundary layer both are same when the Prandtl number is 1. So Prandtl number is nothing but kinematic viscosity divided by the thermal diffusivity. Okay, so if the Prandtl number is 1, then both thermal boundary layer and the momentum boundary layer both are coinciding. In fact, if you look at air has a Prandtl number around 1. It is 0.69, which is very close to 1. So in case of air, you will see that the thermal boundary layer and the velocity boundary layer are more or less coinciding with each other. Okay, so when Prandtl number is less than 1, momentum boundary layer is within thermal boundary layer. When Prandtl number is greater than 1, then thermal boundary layer is within momentum boundary layer, and when Prandtl number is equals to 1, thermal boundary layer coincides with the momentum boundary layer. Okay, up to this we have seen. Also we have seen one more example of this, flow past a cylinder. So when there is a flow past a cylinder, what we have seen is that the velocity is here 0, and then as we move here, somewhere here there is a separation point takes place. So beyond this there is a backward flow is taking place. So if you look at how the local heat transfer coefficient is distributed, you will see that up to this point the local heat transfer coefficient decreases because the thickness of the boundary layer increases. So typically the heat transfer coefficient is K by delta. Since the thickness of the boundary layer is increasing up to this point, K by delta, which is nothing but heat transfer coefficient roughly, will be decreasing. So that's why the heat transfer coefficient or a Nusselt number is decreasing. But beyond this particular point, uh, since because of the backflow and the turbulence added by this backflow, the heat transfer coefficient after this starts increasing. Okay, so what we are trying to appreciate in this slide is the heat transfer coefficient is not constant throughout this flow, isn't it? It is changing, isn't it? So very often we calculate an average heat transfer coefficient and we report the average heat transfer coefficient correlations for a particular geometry. So you will see that most of these correlations which are given for the heat transfer coefficient, these basically gives you an average heat transfer coefficient rather than a local heat transfer coefficient. So this we have seen in the last class. So is there any question so far? Hello?
No, sir.
Okay. Okay, so towards the end of the last class, we started saying something about the dimensional analysis. So what we said is, so far what we are discussing is the heat transfer coefficient we need to calculate. How we are going to calculate heat transfer coefficient? By using the correlation. But somebody has to make these correlations, isn't it? Somebody has to generate these correlations. So how people are generating these correlations? They first generate the data by varying the shapes, different shapes, velocity, and different fluids, isn't it? Based on that, they develop the correlations, and these correlations are then used for finding the transfer coefficient. Okay, but whether these correlations should have the specific dimensionless groups or not, that's a very important question. Okay, so dimensional analysis is a powerful tool to identify dimensionless groups which are used to correlate the variables that influence a particular physical process. This is a very important thing to look at. Okay, so typically if we look at any heat transfer system, in that heat transfer system, based on our experience or based on our understanding of the process, we can clearly say that what are the different variables which are important. For instance, if you are looking at the pipe flow, in a pipe flow, we based on the data we can clearly say that the heat transfer coefficient, velocity of the fluid, diameter of the pipe, thermal conductivity of the fluid, specific heat of the fluid, rho, which is nothing but the density of the fluid, and viscosity of the fluid. All these parameters are important. So only this much information is required. Once we know this, then we can use the dimensional analysis and we can figure out what are the different dimensionless groups one need to look at in order to correlate one of these variables, isn't it? So in this case we are interested in correlating heat transfer coefficient, so we can pinpointedly can find out how this heat transfer coefficient can be correlated to different dimensionless groups which will be comprised of these variables. Okay, so so there is a theorem which is called as Buckingham Pi theorem. Buckingham Pi theorem, named after the scientist Buckingham. What he is saying, if the equation phi which is a function of different variables x1, x2, xn equals to 0. So this is the equation of state, isn't it? This is in a way is the equation of state. So if all these variables are related with each other in terms of one relation, whatever, isn't it? And we are saying that this relation among x1, x2, xn, it holds for any choice of units, then the solution of this equation can be represented in terms of a dimensionless group. So we can represent this original equation phi x, which is function of x1, x2, xn, as as equation, another equation which is function of pi1, pi2, pi m. Okay, where pi1, pi2, pi m are the dimensionless groups. Okay, that's what this Buckingham pi theorem is saying. So again, how many dimensionless groups one can have? That can be obtained using this equation, n minus m equals to p, where n is the number of variables, m will be the number of dimensionless groups one should get, and p is the number of fundamental quantities which is being used in these equations. Is it clear to everyone what I'm trying to say? Hello? Hello?
Yes, sir.
So these things will be clear to you once we look at the specific example on this. Okay, so let's look at the dimensional analysis of convective heat transfer to a fluid flowing through circular pipe. Okay. So as I said in the last slide itself that the heat transfer coefficient, velocity, diameter of the pipe, thermal conductivity of the fluid, specific heat of the fluid, density of the fluid, and viscosity of the fluid. These are going to be the variables which will be, which will completely define the heat transfer in the flow through a circular pipe, isn't it? So we can write a equation of state in this case as phi hv dk cp rho mu equals to 0. Do you all agree? What does this means is all these variables are related with each other. That's what it means. Is it clear to everyone from where this equation 1 is coming?
Yes, sir.
So what we are saying is heat transfer for a fluid flowing through a circular pipe is completely governed by these 7 variables. That's what we are trying to say by using this equation number 1. Now, in this case, we can write down what will be the dimensions of each of these variables. So H is given by what? H is given by watt per meter square degree Celsius, isn't it? Again, watt we can write down as joule per second. So that can be written as again kg per meter square second cube per second cube, isn't it? So we can write down this in terms of a fundamental quantity. So remember here, kg is the unit of mass, meter is a unit of length, and second is a unit of time, isn't it? So we have to write the units of all these quantities in terms of fundamental quantities. So what are the fundamental quantities? There are 7 fundamental quantities: mass, length, time, temperature, current, and then luminous intensity is there, isn't it? Correct. So these are the and moles. Okay, so these are the 7 fundamental quantities are there. Now we wanted to write each of these variables in terms of their fundamental quantities. So that's what we are doing. H is having a unit of watt per meter square degree Celsius. So we are representing. So here watt is nothing but joule per second, and this joule we can write down in terms of kg per meter second, kg per meter square second square, isn't it? So this watt will be given by nothing but kg per meter square second cube per second cube, isn't it? So the unit will be what? Kg means mass, so that is written as capital M, isn't it? This small t is given for time, so we are having per second cube is there, so that means t raised to the power minus 3 we will have, isn't it? Okay, so again in this case, this meter square will get cancelled out. Remember, if I put this watt here, so this meter square and this meter square will get cancelled out. So ultimately what we are going to get is the unit of H will be kg per degree Celsius per second cube, isn't it? That's what we are going to have the unit for H. So therefore, the dimension of the H will be m t raised to the power minus 3 capital T raised to the power minus 1. So this capital T raised to the power minus 1 is per degree Celsius. That is quantifying per degree Celsius. Is it clear to everyone? Hello?
Yes, sir.
Yes.
Similarly, the dimension of velocity also we can write down as that is meter per second, isn't it? So meter is given by length L, isn't it? And per second, so T inverse. Again, diameter will be given by unit meters, so that is directly given as L. Thermal conductivity again watt per meter degree Celsius. So this watt again we can put it from this here, and based on that again we can calculate the dimensions of K. So that comes out to be mass, length per time cube and per temperature, isn't it? So the time per time cube will be T raised to the power minus 3 and per degree Celsius will be given by capital T raised to the power minus 1. Specific heat is again given as joule per kg per second, joule per kg per degree Celsius. So here also joule we can replace by this, isn't it? Joule is given by what? Kg meter square per second square, that we can replace. So again we can calculate the dimension of specific heat. That comes out to be L square T raised to the power minus 2 capital T raised to the power minus 1. Similarly, the density will be given as kg per meter cube. So it's a straightforward way we can write down. Kg is just mass, so m meter cube per meter cube, so L raised to the power minus 3. And viscosity kg per ms, so that is again m L raised to the power minus 1, T raised to the power minus 1. So in this manner, we can find out the dimension of all these variables in terms of fundamental quantities. Does it make sense to everyone?
Yes, sir.
Now, in this case, we are having 7 variables, but how many fundamental quantities we have used here? See, there are total 7 fundamental quantities, but in this case, we are using only 4 fundamental quantities, isn't it? Mass, length, time, and temperature. These are the only 4 quantities we are using. So based on this, we can clearly find out how many dimensionless groups we can have, isn't it? So there are 7 variables. Fundamental quantities we are using is 4. So 7 minus 4. So that means we will have only 3 dimensionless groups will be formed, which can relate with each other to show the relationship between all these variables. Do you all agree?
Yes, sir.
So please repeat this again.
Okay, so there are 7 variables are there: H, V, D, K, Cp, rho, and mu. And these 7 variables, when we are representing their dimensions using a fundamental quantities, the only 4 fundamental quantities I am using: mass, length, time, and temperature. I am not using luminous intensity here anywhere. I am not using current here. I am not using moles here, isn't it? So out of 7, only 4 fundamental quantities I am using. And remember in the last slide what we said, n minus m equals to p. That means n minus p equals to m, where m is the total number of dimensionless groups I can have. So in this case, p is what? How many fundamental quantities I am using? 4. N is what? 7. So 7 minus 4 will be m. So what value of m I'm going to get? 3. Is it clear?
Yes, sir.
So let's assume that these 3 dimensionless groups are pi 1, pi 2, pi 3. Okay. So now let's represent these 3 dimensionless groups here. So pi 1, pi 2, pi 3, and I am representing this in terms of the variables. So I am having 7 variables. So in every dimensionless groups I can represent okay. So in this case, 7 variables are there, but I can have only 3 equations, isn't it? There are only seven variables, but I can write only 3 equations in terms of pi1, pi2, pi3, isn't it? So that means what? The three variables will be unique in these 3 equations. Do you all agree? All other 4 will be repeated. Do you all agree? Yes or no? Remember, there are 7 variables are there, but I can write only 3 equations. So clearly 4 variables will be repeated in each of these 3 equations. Yes or no? Correct? Does it make sense or not? Please say so. Something. I am saying I have a 7 variables, but I wanted to represent this using 3 equations. So clearly 4 variables will be repeated in each equation.
Yes, sir.
So I am kind of selecting that K, mu, rho and D will be repeated in these 4 equations. It's not necessary to select only K, mu, rho and D. Any 4 you can take, and the other 3 will be varying. I have selected this arbitrarily. This is an arbitrary choice. There is no rule. Any 4 variable you can take common, and the remaining 3 will be varying in these 3 equations. Okay, I have selected in this case K, mu, rho and D, and that's an arbitrary choice. Even though you take any other 4 variables repeating in these 3 equations, still you will get the same answer. It's not going to change your answer at all. Is it clear to everyone?
So why can't we use all the variables in one equation and different number of variable in another?
So then if you use all the variables in this equation, then pi1, pi2, pi3, all 3 will be same. Yes or no?
No, then in second we can use 6 variable and third we can use another.
Okay, so what you are saying? In the pi1 we will have all 7, pi2 we will have only 6, and pi3 we will have only 4. Okay, all right. But that cannot be done. That cannot be done. As per this, Buckingham Pi theorem, we have to use the dimensionless groups should be having the same number of variables. Of course, some of these variables, okay, so see, some of these variables, if you look at it, their contribution is going to become 0 if you solve this. But this is a specific the formation of the equation is specific in term. The formation of this equation is specific in Buckingham Pi theorem. So I will not be able to have all 7 variables here, 5 here, 6 here and 5 here. That type of is not there. You will have to take any 4 as a common depending. So see, for instance, let's say if I would have had 3 fundamental quantities here, I would have had 4 equations, isn't it? In that case, I would have had 5 common and 1 varying. Okay. So the formation of pi1, pi2, pi3 or any of these dimensionless group has some rules. It's not completely arbitrary. It is arbitrary in the sense that which common variables you can take, that you can select out of all these variables. That is the only arbitrary thing. Other than that, the specific forms, there is a specific specific rule for that. It's not arbitrary. So pi1, pi2, pi3 I can have like this only, where the 4 will be common and 3 will be varying because only 3 equations I am having. But let's say if I am having only 2 equations, in that case I would have had 5 common and 2 varying.
Okay. Yes.
All right. Okay. So now how it is represented. So here all these variables which I have selected, these are represented in a power. So pi1 is represented as k raised to the power a1, mu raised to the power a2, rho raised to the power a3, and d raised to the power a4, h raised to the power a5. Similarly, pi2 will have different exponents b1, b2, b3, b4, b5. And pi3 will have different exponents as C1, C2, C3, C4, C5. So representing the pi 1, pi 2, pi 3 like this. This is a standard procedure. Okay. So we will not have any deviation with respect to that. The deviation what we can have is instead of k, mu, rho and d which are taken as a common, I could have taken h, mu, d and rho as common and k as varying here. Got the point?
Yes, sir.
So see here I have taken k, mu, rho, d as common in three equation and h, cp and v is varying across these three equation. But I could have taken k, cp and v as varying across three equation. That's perfectly all right. That's perfectly all right. But the pi 1, pi 2, pi 3 will be represented in a specific form as shown here, where each of these variables will be represented in a power. So k raised to the power alpha 1, mu raised to the power alpha 2, etc. Okay. Is it clear? At least how the formation of pi 1, pi 2, pi 3 is?
Yes, sir.
Okay. Now this pi 1, pi 2, pi 3 will have a 0 dimensions. This will have a 0 dimension. So you can put, you can represent all three equations in terms of dimensions now. Okay. So pi 1, pi 2, pi 3 will have a 0 dimension. So let's do it for pi 1 first. So pi 1 will have a all 0 dimensions. So what are the different fundamental quantities being used here? Mass, length, time and temperature, and all four will have a 0 dimension. So pi 1 will have m raised to the power 0, L raised to the power 0, T raised to the power 0 and capital T raised to the power 0. Now k, what is the dimension of k? Dimension of k is this, isn't it? M L T raised to the power minus 3, capital T raised to the power minus 1. So that is put as it is, raised to the power alpha 1. Similarly, mu raised to the power alpha 2, then rho raised to the power alpha 3, then d raised to the power alpha 4, and then h raised to the power alpha 5. And in this equation now, we can compare their individual dimensions. Remember, left hand side, the all dimensions are 0. So now I can compare the dimensions of m, I can compare the dimensions of L, I can compare the dimensions of T, I can compare the dimensions of capital T. So based on whether I am looking at capital M, which is nothing but mass, I can equate this. See here, how many M's I am going to have in the first equation? Just alpha 1, isn't it? So alpha 1 plus this alpha 2. Remember, if I if I combine this, so M here alpha 1 and M here will be alpha 2. I can combine this as what? M raised to the power alpha 1 plus alpha 2, isn't it? So that's why the summation is coming here. Okay, so I am comparing all the exponents here. So alpha 1 plus alpha 1 here plus alpha 2 here plus alpha 3 here. There is no M in the fourth term, isn't it? But there is a M in the fifth term. So only alpha 5 I am going to have, and that should be equals to what? 0. Can you see how I have formulated equation number 2 here? Hello?
Yes.
Yes, sir.
I am only comparing the exponents. I am saying all these pi will have pi 1, pi 2, pi 3 will have a 0 dimensions. Then I am going to compare the dimensions of each of these fundamental quantities in these equations. Okay, so I will have 4 equations here. Okay, so similarly I can write down the equation for L. So here L in the first term here, the exponent of L will be what? Alpha 1. Here in the second term, the exponent of the L will be what? Minus alpha 2. Here minus 3 alpha 3, isn't it? Here alpha 4, and there is no length dimension in the fifth term. So we will have alpha 1 minus alpha 2 minus 3 alpha 3 plus alpha 4 equals to 0. Similarly, we can compare the dimensions for time. We will get minus 3 alpha 1 minus A2 minus 3 A5 equals to 0. And finally for temperature, we will have minus alpha 1 minus alpha 5 equals to 0. Now remember, in all three equations, these last three variables are varying, isn't it? So what we are going to do is we are going to represent all these exponents alpha 1, alpha 2, alpha 3, alpha 5 in terms of alpha 5. Similarly, in the second equation, we are going to make beta 1, beta 2, beta 3, beta 4 in terms of beta 5. Similarly, C1, C2, C3, C4, we will represent in terms of C5. Isn't it? In this case,
Sir,
please go
so
ahead.
so in the previous slide, so what is the importance of A1 minus A5 and B1 minus B5 and C1 minus C5 are unknown constants?
These are unknown constants. We are going to find out their values by comparing the dimensions.
So the value of
Oh,
A1 minus A5.
We are going to find out their values because that is what going to give us the dimensionless groups. What we said is, in this slide, what we are saying that there are 7 variables. We have found out their dimensions in terms of fundamental quantities. What we said is there are only 4 fundamental quantities being used. Based on that, we have found out how many dimensionless groups we can have. So we got 3 dimensionless groups. So these 7 variables then we have rearranged in these 3 groups. Here we have taken, since there are 7 variables and 3 equations, so clearly 4 will be common and 3 will be varying. So the 3 varying will be H, Cp and rho, and that's an arbitrary choice. We could have taken any of these variables, doesn't matter. Okay. Then each of these variables which we have represented with the exponent, and what we are saying that these exponents we don't know, isn't it? And their multiplication is going to give me a dimensionless group. That's what we are saying. So that's why dimensionless pi 1, pi 2, pi 3 are the dimensionless groups. So therefore, what will be the dimensions here for the fundamental quantities for pi 1, pi 2, pi 3? 0, because these are dimensionless groups, isn't it? So that's why we have kept this pi 1, pi 2, pi 3. Their units are dimensionless here. Here you can see m dot, l dot, t dot, M0, L0, T0 and T capital T0. So here dimensions of pi 1 is what? There's no dimension, it's dimensionless. That's why all the exponents are 0 here. And the individual dimensions we have put for the remaining variables here on the right hand side. And based on that, now we are comparing their individual dimensions. Okay, just a minute.
Yes, sir.
Just hello. Okay, sorry. So is the slides visible to everyone? Hello?
Yes, sir.
Okay. So now here we are comparing their dimensions. So after comparing the dimensions, how many equations we are going to get here? 4 equations. But how many exponents are there? How many unknowns we are having in this equation? A1, A2, A3, A4, A5. 5 unknowns are there, but we can have only 4 equations. So in this case, the variable which is varying in all 3 dimensionless groups, that exponent we have to, all other exponents we have to represent in that particular exponent. So here this A5 is corresponding to the variable which is varying here, isn't it? So we have to represent alpha A1, A2, A3, A4 in terms of A5. So that's what we are doing. So from this fifth equation, we can write A1 equals to minus A5, isn't it? A1 equals to A5. Correct. Again, from this fourth equation, this A1 and A5 both are, nearly the same here, isn't it? Both are same. So that means A2 will be 0. Similarly, we can find out A3 equals to 0 and A4 comes out to be A5. Okay. Now let's put all these exponents in this equation. So pi 1 will be what? K1 raised to the power alpha 1, mu raised to the power alpha 2, rho raised to the power alpha 3, d raised to the power alpha 4, h raised to the power alpha 5. Now what is alpha 1? Alpha 1 is just minus A5, so that we have put minus A5. What is what is A2? A2 is 0, so that we have put mu raised to the power 0. What is A3? A3 is again 0, so that rho raised to the power 0 we have put. And what is A4? A4 is again A5, so that we have put d raised to the power A5, and h raised to the power A5, that will remain as it is. So here this mu and rho, these are having the exponent 0. So their value is what? Just 1, isn't it? So what we can write down from this? we can write down from this as hd by k raised to the power alpha. Can you see? Yes or no?
Yes, sir.
And now hd by k is what? hd by k is a Nusselt number, isn't it? So this first dimensionless group which we have obtained here is a Nusselt number. So hd by k is a Nusselt number. Okay. Now let's look at the second equation for pi 2. So we are now comparing the exponents for pi 2. So we have again put all the variables here and their exponents as b1, b2, b3, b4, b5, and left hand side again we will have pi 2. So pi 2 is a dimensionless group, so it will have dimensions m raised to the power 0, l raised to the power 0, t raised to the power 0, and capital T raised to the power 0. We can again compare their exponents for mass, length, time, and temperature. So by comparing the exponents, what we get is b1 plus b2 plus b3 equals to 0. That is equation number 8. Similarly, when we are comparing the length, what we are going to get is b1 minus b2 minus 3b3 plus b4 plus 2b5 equals to 0. Then equation 10 is minus 3b1 minus 3b2 minus 3b1 minus b2 minus 2b5 equals to 0. And the last equation I am going to have minus b1 minus b5 equals to 0. This is by comparing this temperature T. Okay, so again from this equation 8 to 11, we can say from equation 11 we can write b1 equals to minus b5. Okay, that we can put it in equation number 10. If I put this b1 equals to minus b5 in this, b1 equals to minus b5, we can find out what is the how b2 is related to b5. Okay, so b2 comes out to be b5. Remember, in this case also we are representing all these b1, b2, b3, b4 in terms of b5. Why b5? Because b5 is the exponent corresponding to a variable that is varying across the equation, isn't it? Yes or no? That's why we are representing in terms of b5. Is it clear to everyone?
Yes,
or
sir.
no? Remember, in this case also we have represented in terms of a5. Why a5? Because this is the last variables are varying. That's why we have done it in terms of a5. And why a5 and b5? Because these are going to give you 4 equations. But there are how many exponents are there? 5 exponents are there. Okay. So in this case also, if you solve these 4 simultaneous equation, what you are going to get is b1 you are going to get as minus b5, b2 you are going to get as b5, b3 will be equals to 0, and b4 will be again equals to 0. Now put all the exponents in this equation. Pi 2 is given as k raised to the power b1, mu raised to the power b2, rho raised to the power b3, d raised to the power b4, and cp raised to the power b5. If you put all these exponent values here, so b1 is what? B1 is minus b5, so that is what we have put, minus b5 here. Mu raised to the power again b2 is what? Just b5. Rho 0, d 0, and cp again raised to the power b5 itself, because that is what is there, isn't it? This cp. Correct. Now in this case also, if you rearrange the terms, what we are going to get? Mu cp by k. So what is this number? Cp mu by k is what? Cp mu by k is a Prandtl number, isn't it? So in the previous case, which number we have obtained? Nusselt number we have obtained here. Here what number we are getting? Here we are getting Prandtl number. Okay. Now let's look at the third equation. In the third equation also we have compared the exponents, and these exponents are then represented in terms of C5. Okay, so these exponents are represented in the C5. What we are getting is here what we are getting is C2 is minus C5, C3 is C5, C1 is 0, and C4 is C5. Isn't it? That's what we are going to get by comparing the exponents here in the third equation. And again, if you put it in the this particular equation, so pi 3 is given as k C1, mu raised to the power C2, rho raised to the power C3, d raised to the power C4, and v raised to the power C5. You can put all C1, C2, C3, C4 here. So k raised to the power C1, C1 is 0. Mu raised to the power C2, so C2 is minus C5, so this minus C5. Rho raised to the power C3, so C3 is just C5. and d raised to the power C5u. So C5u will be there. Again, v raised to the power C5 will be as it is finally. If we rearrange everything, what we are going to get? dv rho by mu. So this is nothing but a Reynolds number. So from these three equation, what we can say? The heat transfer in a pipe flow is related by using these three dimensionless groups: Reynolds number, Prandtl number, and Nusselt number. Do you agree?
Yes, sir.
So if we wanted to completely govern or define the heat transfer in a flow through a circular pipe, then it will be related by only these three dimensionless groups: Reynolds number, Prandtl number, and Nusselt number. And therefore you will see that all the correlations developed for heat transfer through a pipe flow, these are always represented using this three dimensionless group. You will not get any other dimensionless group when we are talking about the flow of a fluid through a circular pipe. You will see all the correlations given in terms of these three dimensionless groups only. So that is the rationale behind. So what information we are getting from this? We are getting the information that when we are developing the correlations for heat transfer for a circular pipe, this should be represented only using these three dimensionless groups. There will not be any other dimensionless group than these three. Okay. So again, this much information we have got through a Buckingham pi theorem. Okay. But the similar expression we can get if we assume a power law dependence between H and the remaining variables. Let's say if we assume that H is related to all other variables: thermal conductivity, viscosity, rho, d, Cp, and V, as a power law as given by this equation. H is given as Ck raised to the power beta 1, mu raised to the power beta 2, rho raised to the power beta 3, d raised to the power beta 4, Cp raised to the power beta 5, and V raised to the power beta 6. If we assume this relation a priori as a power law, then also we can compare their exponents. If we compare their exponents, so H will have these dimensions: K, mu, rho, d, Cp, V, all will have individual dimension, and this dimension raised to the power beta 1, beta 2, beta 3, beta 4, beta 5, and beta 6 we will have. Again, we will compare their exponents. After comparing these exponents, we are representing. So in this case, how many equations we can get? Again, we can get only 4 equations. But how many exponents are there? 1, 2, 3, 4, 5, and 6 are there, isn't it? So the remaining 3, B4, B5, B6. Okay, so B1, B2, B3, B4, this will be represented in terms of B5 and B6. So that's what we have done. We have represented B1, B2, B3, B4 in terms of B5 and B6. So if we compare the exponents in this case, we are going to get beta 1 equals to 1 minus beta 5. We are going to get beta 2. Beta 2 also we have calculated somewhere. Let me just check. Beta 2 we are getting beta 5 minus beta 6. Beta 3 we are getting as beta 6. And similarly, beta 4 also we can get as beta 6 minus 1. And these exponents again we can put it in this equation. So by putting in this equation, what we get? H is given as Ck raised to the power 1 minus beta 5, mu raised to the power beta minus beta 6, rho raised to the power beta 6, and d raised to the power beta 6 minus 1, Cp raised to the power beta 5, and V raised to the power beta 6 itself. And if we rearrange all these exponents, what we are going to get? Hd by k, that is given as Cp mu by k, and dv rho by mu. So typically you will see that when we are looking at the circular fluid flowing through a circular pipe, we get the correlations like this. Nusselt number is given as C raised to the power Prandtl number, C into Prandtl number raised to the power some exponent, and Reynolds number raised to the power some exponent. So typically for a turbulent flow, the correlation given is a Dittus-Boelter equation, which is given as Nusselt number is equals to 0.023, Reynolds number raised to the power 0.8, and Prandtl number raised to the power 0.4 or 0.3, depending on whether we are looking at heating or cooling. So this type of correlation we have obtained here, a specific form of the correlation we have obtained. Remember, in this case, this is a specific form we have obtained because we have started with a specific form here. We have started with a specific form here. Just a minute. So we started with this specific form here, and therefore we have obtained a specific form after solving it. Okay, but in this case we have started with the specific form and solved. But remember, in earlier case we have not assumed any form. So in this case, using a Buckingham Pi theorem, we are only getting the information that the Reynolds number, Prandtl number, and Nusselt number are related with each other. But how these are related, whether there is a power law relation or whether there is some other relation, all such things are never. You cannot obtain such things using a Buckingham Pi theorem. So Buckingham Pi theorem is silent on the specific form of the equation. It only tells you that what are the different dimensionless groups are going to be there and how these are related with each other. That part is Buckingham Pi theorem is not at all saying. It is silent on that. But in this second case, we have solved the same problem, but with the assumption that these are related as a power law. And since we are starting with a power law relation, that's why we are getting a specific form here. But Buckingham Pi theorem does not give you a specific form like this. So that's what it is written here. So experimental heat transfer data in turbine flow are mostly correlated in the form of above equation. This equation. It should be noted that dimensionless analysis does not tell us how the dimensionless groups in particular problem are related. In other words, it is silent about the possible functional form of the correlation. In equation 20, we arrived at a specific functional form because we assumed a power law type dependence at the beginning. Is it clear? Hello? Hello? Yes, is it clear to everyone? Yes, not clear? Please say so. If something is not clear.
Could you repeat this?
Which part?
So the last power law. So the last paragraph.
Okay, so what we are saying here is most of the heat transfer coefficient which you see for a flow through a circular pipe, this has the relation something like this. Okay, so this type of relation we have obtained even using a dimensional analysis. If we start with the power law equation for H like this, otherwise no. But this is an assumption. We started with some assumption here. But in Buckingham Pi theorem, we don't use any assumption. In Buckingham Pi theorem, we don't start with a power law equation like this. In a Buckingham Pi theorem, you can see that we are defining pi 1, pi 2, pi 3. But whether this pi 1, pi 2, pi 3 are related with each other or not, that we are not going to find out. So remember, in this entire analysis, we have only obtained the information that there are 3 dimensionless groups. And these 3 dimensionless groups are what? Nusselt number, which is we have obtained here. Isn't it? Then we said we have obtained Cp mu by K, which is nothing but a Prandtl number. And then in the last, we have obtained the Reynolds number. So what we are saying is Nusselt number, Prandtl number and Reynolds number are related with each other. But in what way these are related, that we will not be able to find out using a true dimensional analysis. Dimensional analysis. But what we have done in this additional exercise which we have done here, we started with some relation. We started with some power law relation. So this is the assumption which we have started. No such assumption we have used when we have started in a Buckingham Pi theorem. But here we started with this assumption. And then we have again compared the individual dimensions of each of these variables. And finally what we have obtained is this relation, which is often seen in the practical cases. Okay, so this relation we are saying we have obtained because we have started some relation here. Okay, but if you don't start with any relation, then we are going to get the information that only Nusselt number, Prandtl number and Reynolds number, these are related with each other. Only this much information we will get. But how these are related, whether these are related specifically like this equation, or whether they will have a logarithmic relation, whether they will have some exponential type of relation, that we are not at all saying. Okay, So dimensional analysis gives only the information that what are the dimensionless groups which are going to be related with each other. How these are going to be related with each other, that part we don't get using the dimensionless analysis. Is it clear to everyone? Is it clear or
Yes,
still
sir.
not clear?
Yes, sir.
Still not clear?
No, sir, it's clear.
No, that confidence is confidence is lacking.
Assume-
Clear?
So we write the beta 1, beta 2 and beta 3 in form of beta 5, beta 6.
Beta 1, beta 2, beta 3, beta 4 we are writing in terms of beta 5 and beta 6 because in this case if you compare the dimension, how many equations we are going to get? We are going to get 4 equations, isn't it? Because there are only 4 dimensions: mass, length, time and temperature. So we are going to get 4 equations. But how many exponents we have? We have 6 exponents here. So that means what?
We have to write in two.
We have to obtain beta 1, beta 2, beta 3, beta 4 in terms of the remaining 2 exponents, isn't it? We have selected beta 4 and beta 5 and beta 6 arbitrarily. You could have obtained beta 3, beta 4, beta 5, beta 6 in terms of beta 1 and beta 2 also. Doesn't matter. Yes or no?
Yes, sir.
Does it make sense to everyone? See, I have calculated in terms of beta 5 and beta 6, all these, but I could have done beta 2, beta 3, beta 4, beta 5, beta 6. I could have calculated in terms of beta 1 and beta 2. Doesn't matter. Still, you would have got the same relationship like this. Is it clear?
Yes, sir.
Okay. All right. Okay. So let us look at some of the dimensionless groups. So far we have said there are dimensionless groups which are important. Now let's look at some dimensionless groups which are regularly we are going to use in heat transfer. So first dimensionless group is Nusselt number. Nusselt number is defined as HD by K. So physically what it means is it is nothing but a ratio of wall temperature gradient divided by temperature gradient across the fluid in the pipe. And let's derive this also. Okay, so consider a heating of a fluid while it flows through a pipe of a diameter d. So you are having a pipe flow through a circular pipe having diameter d. Again, at any axial position, let's say the wall temperature is TW. So temperature of the wall of the pipe is TW and the bulk temperature is, let's say, TB. And we are assuming that the wall is at a higher temperature. So TW is greater than TB. So what will happen? The heat will be transferred from wall to the bulk of the fluid. Is it clear to everyone? The system? System is clear to everyone?
Yes, sir.
So heat flux at the wall will be given by what? So heat flux in this case will be given by what? Heat flux at any radius r will be given by what? K dt by dr, isn't it? And when we are saying a wall heat flux is what? Wall heat flux is nothing but K dt by dr at r equals to r. R is, so in this case r is the radius of the pipe, isn't it? So if I'm calculating the heat flux K dt by dr exactly at r equals to r, then it is nothing but what? It is nothing but a wall heat flux. Do you all agree? Isn't it? This I am calculating at r equals to d by 2. So d is the diameter of the pipe. That means I am calculating this heat flux at exactly at the wall of the pipe, isn't it? So it's nothing but a wall heat flux. Correct?
Yes, sir.
And now the heat flux at the wall will be what? Equals to what? It will be the heat transfer by a convection to the fluid, isn't it? So that will be given by HTW minus TB. This is the heat transfer at the wall will be given by what? Convective heat transfer will be what? H into delta T. What will be the delta T at the wall? TW minus TB. Yes or no?
Yes, sir.
So now
Yes.
rearrange this equation. So okay, so here I can multiply and divide by d. So this right hand side I can write HD TW minus TB by d, isn't it? Now I can take this d on the other side. Okay, I can take this dt by dr divided by TW by TB. So I can rearrange this equation. I can rearrange this equation as HD by K. If I do a HD by K, I can take this K on the other side here. So HD by K I'm going to get, and all other quantities I'm going to move it on the left hand side. So what I'm going to get, HD by K will be given by what? DT by DR, this DT by DR at R equals to D by 2, and remaining term will be what? TW minus TB divided by D. Yes or no? If I rearrange this equation like this.
Yes, sir. Correct.
So this HD by K is a Nusselt number, but Nusselt number is defined by what? DT by DR at R equals to D by 2. So this is nothing but the gradient at the wall. Yes or no?
Yes, sir.
And TW minus TB divided by D means what? The temperature of the, okay. So, so temperature of the wall I have been given minus bulk temperature I know, that temperature difference divided by whatever is the, okay. So this is, let's say, okay. So this is nothing but let's say a pipe. Here I am having a temperature TW and bulk temperature is let's say TB. Bulk temperature is let's say TB. So what I am doing, this entire diameter I am dividing, this difference. So basically what I'm calculating, it's a temperature gradient across the pipe, isn't it? Yes or no? TW minus TB divided by is going to be the temperature gradient across the pipe. Yes or no?
Yes, sir.
So that's what is defined. Nusselt number is nothing but wall temperature gradient divided by temperature gradient across the fluid in the pipe. Is it clear? Physically what it means?
Yes, sir.
Yes, sir.
Now Reynolds number.
Yes.
Now Reynolds number is defined by what? Inertia force by a viscous force. Inertia force is given by what? You will be multiplying A here. Okay. So A here and A here. Okay. So now in this case, what will be A rho V square? What will be A rho V square will be what? Okay. Tell me. Rho will have a dimension of what? Rho will have a dimension of kg per meter cube. Yes or no?
Yes, sir.
Rho is the density, so this will have a dimension of kg per meter cube. And okay, maybe I'll just do it. So rho will be A rho V square. So A will have a meter square multiplied by kg per meter cube. V is what? Meter per second, isn't it? So that will be meter square per second square, isn't it? Correct? Yes or no? So what we are obtaining here? Kg meter second square, isn't it? What is the unit of force? Mass into acceleration, isn't it? So mass will be kg. A is what? Acceleration is nothing but the change in the velocity per unit time. So that will have a unit of meter per second, sir. So both are having the same unit. So this represents what? This term represents inertia force. Do you agree?
Yes, sir.
Yes, sir.
Similarly, the denominator is the viscous force. Similarly, a denominator is a viscous force. The force force because of the viscous resistance. Okay. So this denominator will be again will have a same unit like this. So this will have a viscous force. So now what we are calculating Reynolds number as? Reynolds number is nothing but the ratio of inertia force by viscous force. Is it clear to everyone? So that comes out to be dv rho by mu or lv rho by mu. Doesn't matter what characteristic dimension you are looking at. Is it clear to everyone?
Yes, sir.
Yes, sir.
Now Prandtl number. What is Prandtl number? Prandtl number is nothing but the ratio of momentum diffusivity to thermal diffusivity. Momentum diffusivity is what? Momentum diffusivity in this case is nu. Nu is given by what? Nu is nothing but viscosity divided by density, isn't it? So here nu will be what? Mu by rho. Mu by rho. And thermal diffusivity is what? Thermal diffusivity is what? K by rho Cp, isn't it? So if you rearrange this, what you are going to get? Cp mu by K. Is it clear?
Yes, sir.
Okay. So next dimensionless number is a Stanton number. So these are the dimensionless numbers which you are going to see regularly in heat transfer. So we are discussing all the dimensionless numbers first, so that you know whenever these dimensionless numbers you will see, you will try to relate. Okay. So the next dimensionless number is a Stanton number. Stanton number is defined as rate of wall heat transfer by convection. Rate of wall heat transfer by convection divided by rate of heat transfer by bulk flow. So okay, let's derive this again. So the equation which we get is H by rho V Cp, and that is given as Nusselt number divided by Reynolds number and Prandtl number. But let's derive this number again from the first principle. So if we consider a temperature difference of delta T across the wall and the bulk fluid, okay. So what will be the convective heat flux? Convective heat flux will be given by H delta T. Do you all agree?
Yes, sir.
Isn't
Yes,
it?
sir.
Again, if the fluid flows, let's say if the fluid is flowing with a velocity V, isn't it? So it is going to, this fluid element is going to carry some energy with it, isn't it? So how much heat energy is taken away by a bulk motion? Bulk motion. That will be given by mass flow rate into specific heat into temperature change. So rho V Cp delta T is nothing but what? This is going to give you how much heat energy is taken by a bulk motion of the fluid. And the ratio of these two is nothing but a Stanton number. So that's what we have calculated here. So H delta T is the convective heat transfer, and this is the heat transfer by a bulk motion. So that is given as H by rho V Cp. Again, that is if you put the dimensions of Nusselt number, Reynolds number, and Prandtl number, you will get this as Stanton number is obtained as Nusselt number divided by Reynolds number into Prandtl number. Okay, is it clear to everyone?
Sir, can you please re-explain heat transfer by bulk flow?
So heat transfer by bulk flow is what? It is nothing but when the fluid elements are moving because of the velocity, they are going to carry some heat with them. Isn't it? Correct?
Yes, sir.
So how much amount is moving, that will be given by mass flow rate. Isn't it? How much
Yes,
is the amount of material is moving, that will be given by mass flow rate. Yes or no?
Yes, sir.
Multiplied by specific heat will be what? The energy potential, isn't it?
Yes, sir.
And multiplied by delta T means what? How much the energy.
So delta, why is there is a temperature change like in a moving fluid?
So okay. So fluid is moving from one location to the another location, and both these locations will have a different temperature.
Yes, sir, got it.
Okay. So the total amount of energy transported from one location to the another location will be given by this rho V Cp delta T. So if we are having the pipe flow like this, let's say this is the pipe, how much energy is taken away from this point to this point you can obtain by using this expression rho V Cp delta T, where delta T will be nothing but what? This T1 and this is T2. So delta T will be nothing but the temperature difference between these 2 points. Is it clear?
Yes, sir, yes.
Okay. Again, there is another factor. Again, the heat flux due to conduction across the distance d under the same temperature driving force. Okay, so now here we have looked at this temperature difference here, but let's say we are looking at temperature difference across this diameter here, let's say. across this diameter here. In that case, the heat transfer across this diameter will be given by what? K by D into delta D, isn't it? Yes or no? Yes or no?
Yes, sir.
Sir, why delta T? I mean, why are the temperatures different in that
So
direction?
okay, at the here some temperature you are going to have, let's say T, and wall temperature you might have some TW. So
But
delta
sir,
T in this
written-
case, this delta T will be different. In this case, the delta T will be TW minus T bulk here. Yes or no? Correct?
Yes, sir. Yes, sir. But it's written just here that across the distance D under the same temperature. What does that mean? Under the same temperature.
Okay, so okay, let's assume that this delta T, if you are assuming that the same, okay, this temperature difference is same here across the pipe, but it's not required. We are only assuming that, okay, we are only assuming that this temperature difference we are looking at, this temperature difference and this temperature difference is same. So that means what we are assuming here is this entire pipe flow here, the fluid here is at a stagnant position, isn't it? So if the fluid is at a stagnant position, what we are going to take a delta T as across the radial direction, what you are going to take? The same delta T will be there, isn't it? So this same word is used, only to mention that this delta T and this delta T is same. Okay. Is it clear? Yes or no?
But sir, the temperature difference above in the Stanton number is considered along the length, right? The temperature
No.
difference.
H delta T. Okay, this part is different. No? This is used for calculating this Piclet number, not for this. Up to this is the different part. Is it clear?
That's what I'm saying, that the temperature difference in the above portion is taken to be along the length, right? But below we are saying that it is the same delta T which is used above. But here
Yes.
we are in the Peclet number, we are considering that the temperature difference is along the radial direction. Then how can it be same as
Okay,
that?
so okay, what it is comparing is if the same temperature difference is there in both the cases, what will be the ratio? That is what it is comparing. We start with the saying that this delta T is same. Then what will be the ratio? Still not clear?
No, sir.
Okay, so what we are trying to say here is, okay, you are saying that this delta T, this delta T and this delta T will be different. Yes, of course, this will be different. Yeah,
Yes.
I agree. But we are not asking this question. We are asking a reverse question. What we are asking is, if this delta T and this delta T is same, what will be their ratio? So what I am trying to say is, for a same temperature difference here, what type of resistance I am going to get? And when I am having the same temperature difference here, what type of resistance I am going to get for a convective heat transfer? That ratio I am calling it as a Stanton number. I am asking a reverse question. Is it clear here?
Okay, so we are considering the magnitude of temperature difference to be same. Okay.
I am saying for the same magnitude of temperature difference, this bulk, whatever the resistance I am going to offer for this bulk heat transfer here and the heat transfer here, convective heat transfer here, their magnitude I am comparing with each other for same delta T. Then it is called as a Stanton number.
Yes, sir. Understood.
Similarly, I am calling a Piclet number as for the same temperature difference, I am calculating the convective heat transfer, and I am also comparing the rate of heat transfer by conduction. Conduction will be given by this directly. Yes or no?
Yes, sir.
So then that ratio is called as a Piclet number. So see, remember here we are comparing the two terms. Comparing these two terms for what? Some common basis should be there, na? So that common basis is
Yes.
delta T is same. Isn't it? Whenever we are comparing two terms, we have some common basis, isn't it?
Yes, sir.
So that common basis we are using as is same delta T. Is it clear to everyone now?
Yes, sir.
So the new number is here. When rate of wall heat transfer by bulk flow divided by rate of heat transfer by conduction, when we calculate this ratio is called as a Piclet number. So Piclet number becomes very important when we are looking at the heat transfer of liquid metals. That also we will see subsequently. So whenever we are looking at the heat transfer by liquid metals, in fact, it has several practical applications. For instance, in a nuclear reactor, very often the liquid metals like sodium is used for heat transfer. So in such cases, the Piclet number becomes more important. Okay. All right.
Sir?
Please go ahead.
Sir, I had one query. So the conduction is being considered along the length of the tube, or it is in the radial direction. I just got confused.
Doesn't matter. We are saying both. Conduction can take place in a radial direction as well as in a axial direction. Similarly, the convection can also take place in a radial direction as well as axial direction. Okay.
Okay, so D will vary accordingly.
So yes. Here we have just said D. If you are looking at across the things, then we are taking this as a diameter.
Okay, sir. Thank you.
Okay. So another number is there, the Grad's number. So Grad's number is nothing but Piclet number multiplied by D by L, and this is used for a heat transfer in a laminar flow in a pipe. So this is nothing but a Piclet number itself, but multiplied by D by L. Okay. So laminar, this number is used for laminar flow in a pipe. Okay. So is it clear so far everything?
Yes, sir.
Okay. Now let's look at how the heat transfer coefficients are, formulated. So remember how the data is generated. Basically, what we are trying to answer here is how the data is generated for, developing the heat transfer coefficient. So let's take a simple example of double pipe heat exchanger. So there is a steam flowing through this annular region, and there is a liquid flowing through the inner pipe. Okay. So this liquid flowing through the inner pipe is heated by a steam flowing through this annular region. Okay. Again, the diameter of the inner pipe is D. Length of this double pipe heat exchanger is L. The velocity with which the fluid is moving from this end to this another end is V. Rho, mu, Cp and K. These are the properties of the fluid which is flowing through the inner pipe, and these are calculated at the average temperature. So remember, between these two ends, the temperature is varying as T1 to T2. So average temperature is taken and the properties are calculated at average temperature. Now, in this case, a correlation of heat transfer can be developed only on the basis of a substantial amount of experimental data, experimental heat transfer data for a particular system. So we need to generate lot of data by varying several things. So what are these? So for correlating heat transfer coefficient, experiments should be performed with a large number of fluids. So when we are taking the large number of fluids, what we are going to vary? We are going to vary density, we are going to vary viscosity, we are going to vary specific heat, and we are going to vary thermal conductivity, isn't it? So for instance, we take a water here, sometimes we take a glycerol, sometimes we take some other fluid. So by varying different fluids, we can generate the data for various value of rho, mu, Cp and K. That is the first step. Another thing is we have to vary the diameter of this inner pipe. So multiple double pipe heat exchanger we have to use where the diameter of this inner pipe is varying. Also, the velocity of the fluid flowing through this inner pipe should be varied over a large range. And all this data we have to generate. Okay. So what data we are going to generate? Whatever the exit temperature we are having, that will be the output data. Okay. Now in this case, we can apply the heat balance. So heat balance will be what? Heat gained by the liquid flowing through the inner pipe. So that means this liquid which is flowing through this inner pipe, how much heat this liquid which is flowing through the inner pipe is going to gain from this end to this end. So its temperature is varying from T1 to T2. How much heat will be gained by that? That we can directly obtain by using this particular equation, isn't it? Bulk flow. So pi by 4 d square rho Vcp T2 minus T1. So that is nothing but the delta T we are going to get. So that is nothing but the temperature difference between these two ends multiplied by mass. multiplied by mass flow rate, isn't it? So mass flow rate you can obtain by density multiplied by volumetric flow rate. So that's what we have done. Velocity into area will give you a volumetric flow rate. That volumetric flow rate multiplied to density will give you a mass flow rate. Mass flow rate you multiply to Cp delta T, that will give you the rate of change of energy, between these 2 points. Do you agree?
Yes, sir.
And that should be equals
Yes,
to
sir.
what? That should be equals to how much amount of heat is transferred by a hot fluid to this cold fluid, isn't it? Remember, this hot fluid is flowing through this annular region surrounding this inner pipe, isn't it? So how much heat is transferred by this hot fluid to this cold fluid which is flowing through this inner pipe should be the same as the amount of energy change from this point 1 to 2, isn't it? Here. Do you all agree?
Yes, sir.
So how
Yes.
much sensible heat gained by this cold fluid should be same as how much amount of heat is transferred by a hot fluid to the cold fluid. Now amount of heat transferred by a hot fluid to the cold fluid will be given by what? HA delta T, isn't it? Convective heat transfer, correct?
Yes, sir.
But the problem here is what temperature difference you are going to take. Here the temperature will be at this end, the temperature difference will be what? TW, let's say saturated temperature, steam temperature is, let's say TW. So TW minus T2 will be the temperature here. Yes or no?
Yes,
But
sir.
what will be the temperature here? TW minus T1. So that means delta T is changing across the length of the pipe. It is not same. Isn't it? Driving force for convective heat transfer, which is delta T, nothing but in this case will be TW minus T2 or T1, and that is going to change as I am moving from this left hand side to the right hand side end. Do you all agree?
Yes, sir.
Yes, sir.
So my delta T is not same. My delta T is changing. So whenever my delta T changes along the length of the pipe, in that case, the temperature difference is taken as log mean temperature difference. We will prove this point. Why it should be a log mean temperature difference, we will prove. There is a detailed proof I am going to give you in a subsequent slides. So in all such cases where the temperature difference is varying across the length of the pipe, in such cases the temperature difference is taken as a average temperature, and the average is taken as a log mean temperature difference. So this is going to give you a average temperature difference between both these ends. Is it clear? This part we will prove. But for a time being, you can assume that this is correct. So log mean temperature difference is calculated as what? TW minus T1 will be the temperature difference at this end, and TW minus T2 will be the temperature difference at another end. So both these temperature difference are subtracted from each other, divided by ln of TW minus T1 divided by TW minus T2. This will give me a log mean temperature difference. So this is in a way is nothing but what? This is in a way is nothing but let's say I can represent this as delta T1. I can represent this as delta T2. So this is in a way is nothing but what? Delta T1 minus delta T2 divided by ln delta T1 by delta T2. Okay. This is what we are calculating here, where delta T1 is the temperature difference at the end 1. Delta T2 is the temperature difference at the end 2. And based on that, we have calculated this log mean temperature difference. So now in this equation, everything is known to us. This delta T1, delta T2, we will be able to find out, isn't it? These are known to us. Again, in this case, what is the diameter of the pipe? What is the density of the pipe? What is the velocity of the fluid flowing through the inner pipe? What is the specific heat? Everything is known. We can calculate heat transfer coefficient H. Do you all agree?
Yes, sir.
Now this experiment, this is one experiment. This is one experiment. Now we have to perform several such experiments by having different fluids, by varying diameter, by varying the velocity. If you do that, we will get different values of H. Do you all agree? Yes or no?
Yes, sir.
So then with the values of H, you can calculate HD by K. So that will be a Nusselt number. Similarly, you know D, V, rho by mu for each experiment, isn't it? So you can get Reynolds number. Similarly, Cp mu by K, you can calculate, that will be a Prandtl number. And then you can do a non-linear regression to fit this equation and find out the correlation. That's how the correlation of heat transfer are obtained. Is it clear to everyone? Is it clear to everyone how the correlation of heat transfer can be obtained?
Yes, sir.
Make sense?
Yes.
Yes, sir.
Okay. All right. So there are several correlations developed in the literature. Okay. For various systems. So correlations for heat transfer coefficient. So systems of various shapes and different flow conditions are encountered in practical heat transfer calculations. The common shapes or geometries are cylindrical, spherical, or flat. The most common flow problem involves the flow through a circular pipe. So this is a commonly used system when the fluid is flowing through a circular pipe. But you will also see several other systems where the non-circular duct are used. Non-circular ducts are used, such as flow through channels, flow through rectangular channels, flow through packed beds, flow through agitated vessels with internal, even the jacketed reaction kettle, or even the bank of the tubes. Okay, so there are several such.
Not visible.
Lights are not visible. All right. Is it visible now?
Yes, sir.
So what we are saying is correlations for heat transfer are given for different shapes and different flow conditions. Okay, so systems of various shapes and different flow conditions are encountered in the practical situations. Again, based on that, the correlations are developed. So for instance, we will have a different correlations when we are looking at the cylindrical geometry, when we are looking at a spherical geometry, or whether we are looking at a flat geometry. In all such cases, you will have a different correlations. Also, in addition to these regular surfaces, you will have sometimes in non-regular surfaces like non-circular duct, which could be a flow through a rectangular channel. Very often we see a flow through a packed bed. In a chemical engineering or a process engineering, you will see that the reactants are flowing through the catalyst particles which are packed inside the reactor, isn't it? Flow through a packed system, and in such cases the heat is generated because of reactions, isn't it? So heat transfer also becomes important. So flow through a packed bed, or a flow through a agitated vessel with internals, or even sometimes there is a jacketed kettle is there and the fluid is flowing through the jacket, isn't it? Again, sometimes we are using the bank of the tubes and over which we are blowing the air so that the liquid which is flowing through the bank of the tube should be cooled, isn't it? So all such situations you can see in several practical applications. For all such situations, you will see that the different correlations people have developed. Again, sometimes the flow could be internal, so that means flow is the fluid is flowing inside the pipe. Sometimes the flow is flowing across the pipe, or across the spherical particle, or across the cylindrical particle. So flow could be internal or it could be external. For all such cases, different heat transfer correlations people have developed. So we will start with a very simple case of laminar flow through a circular pipe. So for a laminar flow through a circular pipe, this is what the equation is given by Hansen. So equation given here is Nusselt number is given as 3.66 plus 0.0668 D by L, Reynolds number into Prandtl number, divided by 1 plus 0.04 in the bracket D by L into Reynolds number into Prandtl number, raised to the power 2 by 3. And this equation is valid for Reynolds number less than 2100. Also, here the Nusselt number and Reynolds number, these are defined in terms of the diameter. That's why these are given as HD by K and dV rho by mu. And this equation is valid only for a constant temperature of the pipe wall. This particular thing is extremely important here. This is for a constant temperature of a pipe wall. Fully developed flow and a constant temperature of a pipe wall. Okay. So there is another condition in which we are saying that fully developed flow, but a constant heat flux. For that case, you get a different equation. Again, very often we use only this much equation when my Reynolds number is low. When my Reynolds number is low, then the Nusselt number is given by 3.66. And we can prove this also. We can prove this using a first principle. Again, here you can see that Nusselt number is related with Prandtl number and Reynolds number. But we have not used a power law relation here, isn't it? Because dimensionless analysis tells us what? It only tells us that Nusselt number is related to Reynolds number and Prandtl number. It is not saying anything about the form of the equation. That's why we have used such a complicated form, isn't it? It doesn't matter. Do you all agree with me? Hello?
Yes, sir.
So very often just remember that when Reynolds number is very low, then we are going to use Nusselt number equals to 3.66. That's it. And we can prove this. We will prove this in a subsequent slide. Okay. Also, there is another correlation given by Cedar and Tate. So Cedar and Tate correlation is important when the wall, so if there is a large temperature difference, in that case, the viscosity at the wall and viscosity at the bulk, these two values are different. In that case, we use the Cedar and Tate correlation. So here Nusselt number is given by 1.86 Reynolds number into Prandtl number divided by L by D, and which is raised to the power 1 by 3. And this additional factor mu by mu W raised to the power 1.14. This accounts the change in the viscosity. And this equation is valid only for these three conditions. Similarly, this Hansen's correlation, this is valid only for this condition. Reynolds number less than 2100, that means it is applicable only for laminar flow. These are only for laminar flow. This is also only for laminar flow, but it also requires these additional conditions to be satisfied. Prandtl number between 0.48 and 16700, and mu by mu W is between 0.0044 to 9.75, and Peclet number into D by L should be greater than 10 raised to power 8. So Peclet number into D by L is nothing but what? Gauge number, isn't it? So Gauge number should be greater than 10 raised to power 8. Is it clear to everyone? Yes or no?
Yes, sir.
Okay, so let's stop here. We will continue from this point in the next class. All right. Is there any question so far? Is there any question? So, okay, so if there is no question, I'm going to form some groups, and these groups information I'm going to share you either today or tomorrow, and we can discuss this in the next class. Okay. So groups in the sense that you will have to join your minor examination both by Microsoft Teams and the Moodle. So on a particular Microsoft Teams group, you should have you will have to be online, and you will have to keep your video on, so that at least the TA can see whether you are writing it or not. Okay.